with the particle pairs. So that's encouraging. At short times, as I mentioned, there's not evidence of a very pronounced and extended exponential separation. So now you're seeing in semi-log, so an exponential is a straight line. And you can see that there's no straight line that would fit this all the way from the smallest resolved scales to the Rossby radius of deformation. Whereas certainly for about 1 to 2 days all the way out to when it crosses that and continues on, I can fit it with a single Richardson Law curve. Same curve you saw before in that previous plot. Finite scale Lyapunov exponents, again, remember these would be flat, unchanging with delta if it's exponential separation. Well, at the very smallest scales where I start getting contaminated by a position noise, it flattens out. But at smaller scales, at larger scales, as I move out to a delta of 10, 100, 1,000 kilometers, you can see that it basically goes fairly steep initially to -1 is the best fit for a kind of nice round number, to a -0.6. -0.66 would be what you would expect from Richardson Law behavior, and then starts dropping off more rapidly at a transition of about 200 to 300 kilometers. So, yet again, no evidence of exponential separation at smaller than Rossby radius. So, what's going on there? Well, Lukoska and Ullman argued that what they saw was unequivocally exponential, non-local dispersion, and is consistent with entropy cascade. Basically, what we expect to see when we put these things in the water. As I mentioned, there were some issues with the resolution of the data, though, and it could potentially be contaminating those results at the smallest scales. In the winter Gulf Stream, we see something extremely different. We see basically Richardson Law behavior from 2 kilometers all the way up to 300 kilometers with a Rossby deformation radius around 30 kilometers. So we're seeing this across a long range of scales, including the submesoscale. In other words, it's not consistent with a classic 2D quasi-geostrophic entropy cascade at subdeformation scales. Why is that? One, the hypothesis that I pitched forward in this paper is that there is a significant amount of energy input in the system compared to what you would expect from classic QG turbulence at the submesoscale via instabilities, frontal and mixed layer instabilities in the winter Gulf Stream region. And I argue that this is qualitatively consistent with the kind of surface quasi-geostrophic turbulence theory that a number of people have been talking about for quite a while in the fluid mechanics literature, where you can have surface trapped energy that fills up the submesoscale. You're injecting energy into that, and you're flattening the wave number compared to that classic 2D quasi-geostrophic turbulence curve, flatter than -3, and thus you're getting not exponential but local dispersion at those smaller scales. Now, there have been some more recent studies, and most recently there was this experiment called the Grand Lagrangian deployment done by a number of people at the University of Miami, where they put 300 drifters in the Gulf of Mexico. These are, again, kind of code-style drifters that they built themselves. But they said, look, we don't want particle statistics limitations causing error bars that are going to mess us up. We're going to put a lot of drifters out. They put them in trios of trios, deployed in the region of the Deepwater Horizon spill. They calculated, in this case I'm showing the rate of change of velocity as a function of distance. It's kind of similar to the finite scale Lyapunov exponent. And what you basically see, or what they argue, is compared to the simulation, which flattens out and is consistent with this sort of exponential separation, that the observations follow this r to the -2/3 curve, Richardson Law behavior, across this full range of scales, all the way down to below 1 kilometer. And they argue in their kind of impacts paragraph up front, we show conclusively that ocean flows contain significant energy at scales below 10 kilometers, and that their fluctuations, local dispersion, dictate the initial spread of tracer pollutant clouds. So they basically conclude that this local dispersion, this Richardson Law-like behavior, and not exponential separation driven by those larger scales, is what's really happening at these very small scales. So if you put, say, particles of simulated oil in a model where you're not resolving things smaller than 20 or 10 kilometers, you don't get that submesoscale. You would grossly underrepresent how quickly the cloud would spread, how quickly the oil spill will spread in the first amount of time. So this has some really significant real-world implications. And of course, it's almost immediately been questioned. Baron Vera and Joe Lacoste have a paper submitted, and Javier Baron Vera gave me a copy of it. And in this, they argue that those results were contaminated by the presence of inertial oscillations. They take the trajectories. Here you're seeing this is the Lagrangian structure function, but basically this is consistent with Richardson's law here. If it has this slope, and if it has this slope, it's exponential separation. And this is the unfiltered data. Well, then they take the trajectories and they low-pass filter them to remove inertial oscillations. I wonder how much else they've removed when they do that. When they do that, though, the curves get steeper, and they argue it looks more consistent with exponential separation. This is under a paper that I understand from Javier is under review right now. But basically, they're trying to call into question, again, this issue of what exactly is happening at the sub-mesoscale. And I think it's a nice argument that this issue has not been resolved yet. It's still kind of an active debate right now in the Lagrangian ocean observation world, and we're waiting to see what comes out of this very large data set and maybe what happens with analysis of more drifters elsewhere in the ocean. We have a lot of pairs deployed elsewhere, and it's really ripe, low-hanging fruit for study. So in conclusion, we can quantify stirring and spreading a number of different ways. Very robust way is to use these single particle calculations, and it's robust because you have so many single particles floating around in the ocean to make those calculations with. There is, of course, the issue of the integration timescale, and there's a big debate about how long that needs to be to do this properly. Multiple particle calculations give information about the stirring and the wave number spectrum of the turbulent field, so it's really exciting to start looking at these multiple particle calculations. And there's this really fun debate, controversy. How important is the submesoscale in spreading and stirring? And I think that's kind of the state of the field right now. So thanks for your attention. I think I'm closing at about the right time. Thanks.